Continuity. Okay, wait a minute. Before we even look at this definition, it's not complete. I have to fill in kind of the blank here. Let's think about intuitively what it meant for a function to be continuous for the one input variable function. So for a one input variable function, it's continuous if you can draw it without lifting your pen, right? So this would be an example of a continuous function of the type from calculus 1, y equals f of x, continuous. No holes in it, right? No breaks in the graph, right? That's what it means for a graph to be continuous. Do you remember the definition for a continuous function back in Calc 1? The more formal definition? It involved a limit. If you take the limit of f of x as x approaches a, then not only does that limit exist, but in order for the function to be continuous, it has to equal f evaluated at a. This is how you evaluated a lot of your limits. Remember, you'd use direct substitution whenever you could. Remember that? And the reason you could use direct substitution was because of continuity, because the function was continuous at that a value, whatever it happened to be. So that's the calculus 1 definition of continuity. I guarantee you your instructor showed it to you in calculus 1, but everybody forgets it for whatever reason. So let's fast forward to calculus 3. So continuity, the definition here, we say z equals f of xy is continuous at a point AB, the input point AB, if the limit as xy approaches AB of f of xy, well, what would that have to equal? We're going to fill this in here. F of AB, yes. So not only does that limit exist, it's equal to f evaluated at the point that xy is approaching. And this sort of definition then ensures that there's no holes in the graph, no breaks in the graph. It's a continuous. Now, we don't think of it as a curve anymore. What is it? What does y, or z, I should say, what does z equal f of xy graph to be in space if it's continuous? Well, how could you picture it in your mind? Picture a blanket floating in space, and there's no holes, hopefully, in your blanket, right? No breaks in the graph. So it's a surface, in other words. Z equals f of xy is a surface. The notes on continuity. Note number 1. This definition of continuity allows us to evaluate limits of continuous function using substitution, just like in calculus 1. Okay? So as long as you don't get division by 0, and as long as AB is in the domain of f, then the limit as xy approaches AB, the limit of f of xy as xy approaches AB is just f of AB. Just plug it in. Okay, note number 2, from the limit laws, sums, multiples, and quotients of continuous functions are continuous. Because the limit laws, from the limit laws, you can show that if you're adding, for instance, two continuous functions, if you know that f of xy and g of xy are continuous, right? Individually they're continuous, then you know that the limit of f of xy as xy approaches AB is equal to f of AB if it's continuous, if f is continuous, right? Furthermore, similarly, you know that the limit as xy approaches AB of g of xy is equal to g of AB if g is continuous, right? So the limit laws say, well, what if we take the limit of f of xy plus g of xy as xy approaches AB? Well, then that has to be, if you think about it, let me use a different notation here to help you think about it. When you add the functions together, you could think of it as f plus g, and then put the function notation out here of x plus y. You're not used to thinking of it that way, but that's That's really how you could think about it, because the idea is f plus g is also a function. And, getting ahead of myself there. It should have been comma y. So this is weird-looking function notation. F plus g is a function all by itself of xy, okay? So what do we need to show then? We need to show that this is f plus g of AB if we want f plus g to be a continuous function as well, right? But we know that that's true because the limit laws allow us to break up these the sum into the limit. Now I'm gonna do something I ask you guys never to do. I'm gonna leave off the notation because I want to get you out of here in a reasonable amount of time. I know that this limit breaks up to be the limit of f of xy plus the limit of g of xy, with the assumption that xy is approaching AB. And since I know both of these individually are continuous, I know this is f of AB. I know this is g of AB. So I know the whole thing is f of AB plus g of AB, which is, using the weird-looking function notation, the same thing as f plus g of AB. Looks convoluted, but all I'm saying is, hey, those limit laws allow us to express the limit of a sum as the sum of the limits, and since we know that the individual functions are continuous, then we've shown that the sum of the resulting function you get from the sum of f and g is also continuous. Okay, number 3. Here's the point of that epsilon delta proof that I did. From that last example, we know how to show that f of xy equals x and g of xy equals y are continuous. In fact, if you think about it, if you think about that epsilon delta proof that we did up here, by showing that the limit as xy approaches AB of the function y equals b, we showed that this function is continuous, didn't we? Because all we did, or all it looks like we did anyway, was input AB into the function f of xy equals y, and of course you're just going to get b. In other words, we showed that this limit is equal to f of AB, which is just b in this case. We showed that y is a continuous function, whether you think of it as a one-variable function or a two-variable function in this case. So why does that help us? So from the last example, we know how to show that f of xy equals x and g of xy equals y are continuous. That's the epsilon delta proof. What does that mean? Well, that means since we know that products of continuous functions are continuous, that means that x to some m times y to some n must also be continuous if you extend the idea of the products of continuous functions are continuous. Because x to whatever m power, assuming m is a counting number, or a counting number, assuming, or it could be, m could be 0, so I suppose a whole number. Assuming m is a whole number, x to the m has to be continuous. Y to the n has to be continuous because it's a product of continuous numbers. So x to the m times y to the n is a continuous function. So who cares? Why is that important? So, well, that's important because we can conclude that what are polynomials? Polynomials are sums and differences of multivariable polynomials might be sums and differences of powers of x times powers of y, right? So from that one little epsilon delta proof and the limit laws, we can conclude that polynomial functions are continuous, whether they're multivariable or not. Rational functions are continuous on their domains. You're not allowed to divide by 0, right? But if you think about it, what's a rational function? It's a ratio of two polynomial functions. So, okay, you divide two polynomial functions. As long as you're talking about x and y values that are in the domain, then that's got to be continuous as well, because the two polynomials are continuous. What's the upshot of all this discussion? Well, the kinds of functions that were continuous in Calculus 1, the two variable versions and more, you could have 3 input variables, as many input variables as you want. Those kind of functions are also continuous. Okay, so continuing on with 14.2, does this sound familiar? A composition of continuous functions is continuous? Do you remember what a composition of functions is from like calculus 1? So it's a function of a function, right? So there are ways to take composition in calculus 3 as well. So what is this saying? Let's suppose we have a calculus 3 type function, z equals f of xy. So xy is in the xy plane, right? The R2. But where is z? Z is in R1, right? Z is a number, whereas xy is a point. So xy is mapping. What this function f does is it maps a point like xy to a number like z, doesn't it? So let's suppose that xy, f of xy rather, is continuous at the point AB. Also, let's suppose that we have another function. Now, this is a calculus 1 type function. It has a single input t. Let's suppose that w equals g of t, and also suppose that g is continuous if you make the input values of g range values of f. In other words, there's no reason, since z isn't a single number, there's no reason why you can't, as long as z is in the domain of w, there's no reason why you can't plug in a z value in where the t is, because they're both just real numbered values. So the assumption is that g is continuous in the range values of f. So long story short, f is continuous at AB is really all we need for what I'm about to say. And g is continuous for any input we expect to put in there. Then we should be able to say that g of f of AB is also continuous at AB. Again, that's just a symbolic way of saying that a composition of continuous functions is continuous. So in this example, f of xy is just x squared plus y squared. By the way, what is that graph to be? Think z equals x squared plus y squared. An elliptic paraboloid. Okay. F of xy is x squared plus y squared. Guess what? That's a polynomial, you guys. And so it's going to be continuous for any x and any y value you want to plug in. It's going to be continuous. Polynomials are continuous, right? G of t is equal to the square root of t. That's a square root function, and a square root function is continuous on its domain. In this case, what would the domain of g of t be? T better be bigger than or equal to 0, right? Yeah, we're not dealing with complex valued functions. So the composition I want to talk about here is g of f of xy. So first of all, let's calculate that and then talk about the continuity of it. So what would g of f of xy be? Remember, you work it from the inside out. So what's f of xy equal to? F of xy is this thing, right? So let's work it from the inside out and replace f of xy with its formula, just like you did back in algebra. No different. So we would get g of x squared plus y squared. So the input becomes, now believe it or not, x squared plus y squared is, for any x and y, it's a single number, right? You can think of it as a single t value. So then what do you do next to figure out what the formula for this thing is? You use the function notation. G of t is equal to the square root of t. So it's just telling you whatever the input is for g, you take the square root of it. That's what the square root function does. So g of x squared plus y squared must be what? Square root of x squared. There you go. Square root of x squared plus y squared. So g of f of xy is simply the square root of x squared plus y squared. Now, the other result we want to talk about is what we talked about above. This guy is going to be continuous. And actually, because we're squaring the x and y values, it'll be continuous for all x and y, won't it? Because you're not going to get the square root of a negative number under there, are you? So it's continuous, not just at a particular value a, b, but in this case for all x, y. And we're talking real valued points x, y, right? Okay? So this example did two things. It showed you how to compose. And then the other thing was, well, this turned out composition of two continuous functions is continuous. And this is an example of that. Radical functions, by the way, are continuous on their domains, right? We learned that in Calculus 1. Okay, finally, you're going to see some homework problems like this as well. Find the limit if it exists. The limit as xy approaches 1, 1 of x divided by the square root of x plus y. How do we evaluate that? Yeah, there's no problem with plugging in just x equals 1 and y equals 1, right? You don't get division by 0, that's when you have a problem. So why is that okay to do? Well, it's really because this function is continuous on its domain, isn't it? How is that function formed? It's a ratio of x, which is it's a polynomial, it's a monomial, right? X is continuous. And the square root of x plus y is a composition of the square root function and the polynomial x plus y. And both of those are continuous. The square root function is continuous on its domain, so as long as you don't plug in values, x and y values that give you negatives underneath the square root, that square root function is continuous. You take a ratio of two continuous functions, it's continuous. Why do we care about continuous functions? Because the way you evaluate them is direct substitution. You don't need to write that stuff down, just do the direct substitution. But that's why it works, and it's nice to know why things work the way they do. So this is just going to be equal to, okay, direct substitution 1 divided by square root of 1 plus 1, which is 1 over root 2. Now we have a problem. The limit in part B, evaluate the limit. The limit as xy approaches 0, 0 of x squared minus y squared divided by the quantity x plus y. Can I use direct substitution here? Not directly, no. Any ideas? Yeah, no L'Hopital's rule, you guys. Because what do you take the derivative with respect to, right? You've got two input variables there. No L'Hopital's, but there is an algebraic technique that you learn in Calc 1 you could use here. What would you do?
Oh, just did you factor out?
Yeah, I call it the offending factor. The offending thing is the denominator here, right? Yeah. The quantity x plus y. Maybe we can divide that out if we're smart, right? So the idea is that the numerator factors. So I'm just rewriting it. Don't drop the limit notation. Keep the limit notation. Factor the numerator. X squared minus y squared factors to be x plus y times x minus y. And the offending factor, x plus y, divides out, right? And so we get that this limit is equal to the limit as xy approaches 0, 0 of just x minus y. When is this equality true? Well, let me put it this way. When is this equality not true? So I'm saying this guy is equal to this guy, but when? As long as what? Well, we'd have a problem. This would not be true. This guy would not equal this guy if x and y were both 0, right? Because in fact, the original function does not exist at 0, 0, does it? Okay. But that doesn't matter. When we take limits, we don't actually let x and y get to the a, b value, the 0, 0 value in this case, do we? So it doesn't matter. All right, now do we have a problem with direct substitution? No, x minus y is continuous on its domain. So let's go ahead and plug in 0, 0, and what do we get? So just to show the work, 0 minus 0, which is 0. Now, keep in mind what I'm not saying here. I'm not saying that the original function, so this is f right here, I'm not saying the original function exists at 0, 0. I'm saying the limit as xy approaches 0, 0 of of x squared minus y squared divided by x plus y is 0. It does have a limit. It's just not, the function itself is not defined at 0, 0. So what ends up happening is if you graph f of x, y, there's a hole in the graph at 0, 0. Just a single little infinitesimal little hole at that point 0, 0. So let's let f of x, y be a piecewise defined function. What do I mean by piecewise? Well, you use one formula for certain x, y values and another formula, could be multiple formulas for other x, y values. So let's suppose f of x, y is equal to 3xy squared divided by x squared plus y squared, as long as x, y does not equal 0, 0. And let's suppose that it equals 0, 0 when x, y the function value equals just 0, when x, y does equal 0, 0. Show that f of x, y is continuous at 0, 0. Well, there's something I have to do first to convince you of that. What we really want to show, here's what we have to show then, to show that this function is continuous at 0, 0, this piecewise function is continuous at 0, 0, we have to show that the limit as xy approaches 0, 0 of f of xy, what do we have to show that equals? In other words, the limit value, in order for the function to be continuous at 0, 0, the limit value has to be exactly f evaluated at 0, 0. So really, we can kind of ignore the piece of the piecewise function when xy equals 0, 0, right? Because we just want to focus on the limit as xy approaches 0, 0. And when xy doesn't equal 0, 0, the formula that we use is the rational function 3xy squared divided by x squared plus y squared. So let me focus on that rational function. So let me do this. Let's examine the limit as xy approaches 0, 0 of 3xy squared divided by x squared plus y squared. So I'm going to show you that this limit is 0. I don't know about you, but I don't want to use the epsilon delta proof if I can avoid it. So the way I'm going to show you that this limit equals 0, I'm going to use a trick. Do you remember polar coordinates? Yeah. I would claim that this is the same thing as saying the limit as r goes to 0. Okay, do you remember what x is in polar coordinates? Oh, yeah, good. That's because you just had it last summer, huh? r cosine theta, right? And y is equal to? And we're squaring it, so we get r squared sine squared theta. And then on the bottom, you can go right to just r squared because x squared plus y squared in polar coordinates is r squared. And that's what's going to make this work out. If we didn't have the x squared plus y squared in the denominator, if we had like 2x squared plus y squared in the denominator, it wouldn't work out. So this is a neat trick, but it only works for certain functions. What's going to go away here? So, well, I don't even need, everything's factored, so I could just cross that out, right? So we get the limit as r goes to 0 of what? Just 3r cosine theta sine squared theta? So if you believe that the original limit we're trying to look at is the same as that, then we're in business. Because look, now I'm going to drop the limit notation and say, now, let's see if you believe this statement. This 3r cosine theta times sine squared theta is between two much simpler values. It's between negative 3r and positive 3r. Do you buy that statement? Why would that statement be true? What two values are both cosine and sine always between? No, the function values are always between, think of height values of the sine wave. Yeah, -1 and 1. And so you know that cosine of theta is always between -1 and 1. You know that sine of theta is always between -1 and 1, so sine squared is between -1 and 1. So you take the product of two proper fractions, you get an even smaller number, don't you? Which means the whole thing is between -3r and 3r, right? Okay, so you believe that now? Okay, what does the squeeze theorem say, you guys? Okay, what is the limit of -3r as, remember what r is doing, as r goes to 0? 0. What is the limit? So this is I'll put in parentheses as r goes to 0, right? What is the limit of positive 3r as r goes to 0? 0. So what's your conclusion? So the limit as r goes to 0 of 3r cosine theta sine squared theta must also equal 0 by, what theorem am I using here? Squeeze theorem. So squeeze has an extra e at the end. There we go. So I just did it, didn't I? I just showed that this limit is equal to 0 if you follow the steps. Okay? So why does that help us? Well, remember, all we have to show is that the limit as xy approaches 0, 0, the piecewise defined function is equal to f of 0, 0. But how is f of 0, 0 defined? Well, it's defined piecewise to be 0. So here's the conclusion then. Thus, the limit as xy approaches 0, 0 of f of xy is equal to 0. Because f of xy is equal to that rational function that we just showed the limit is equal to 0, as long as xy doesn't actually equal 0, 0. But we know by the piecewise defined function, oh, I should actually put in that extra thing. We know that f of 0, 0, we know that this limit is 0 by that proof that we just did. And we know that f of 0, 0 is 0 by the way that the piecewise defined function is defined. So what we've essentially done by creating this piecewise defined function, so this function right here, this rational function right here, would have a hole in it at 0, 0. But what does it do by making it a piecewise defined function and saying, okay, yeah, for this guy there's a hole at 0, 0, but let's fill the hole. Let's fill the hole by saying the function value is 0 at 0, 0. And so we've actually created a continuous function even though in the original rational function it had a hole in it. And so it had its discontinuity at 0, 0 is because it's just one little pinprick of a hole. It turns out that that's a fillable or removable discontinuity, if you want to think of it that way. When you graph this thing, you're not actually going to see the hole in the graph, but it would be right here. It would be the point. The hole would occur at the point, well, if you think about it, 0, 0, 0, right? So there would be a hole, if you could possibly see it. If a graphing program were smart enough to put it in there would be a hole right here. But the idea is that that function f fills that hole, okay? So if we're just talking about the rational function, then there's a hole here. But f, by defining f of 0, 0 to equal 0 at that hole, we've filled it. So that's why we call it a removable discontinuity. However, remember earlier we showed that this limit doesn't exist by taking the y equals x path and the y equals 0 path. We showed that limit doesn't exist. So we couldn't create a piecewise defined function that fills the hole. Okay, that thing's not going to be continuous no matter what we do. And when you graph it, there's a telltale sign that the limit simply doesn't exist there. When you get this kind of jagged behavior When you get this kind of jagged behavior near the input of 0, 0, so it does weird stuff here, it drops, there's a big chasm here, comes back. When you get that kind of weird looking behavior, and by the way, if you zoom in on that, it would look the same, then that's a telltale sign that that function is just discontinuous there. Okay? And that kind of discontinuity for an input value of 0, 0 is called non-removable because the limit simply doesn't exist. It's not like one little pinprick of a hole in the graph. There is this big chasm there. Just one quick note, and then we're finished, I promise. I know it was a long lecture tonight. So if you had a 3-input variable function like w equals f of x, y, z, a function with 3 inputs, everything we just talked about holds. You just can't graph it in space, right? Because it has 3 inputs, 4 variables altogether. W, x, y, w is the output, and then x, y, and z. You can't graph that in 3 dimensions. But the limit laws hold. You could generalize the definition, the epsilon delta definition of limit, and the intuitive definition is the one to think of, and that holds as well. Continuity holds. Everything holds for more than 2 inputs. It's just in this class we usually focus mostly on 2 inputs, but not always.